Student, and welcome to this seventh edition of our Numerical Method 2 class. Last time we tackled and we described the algorithm used to solve the Padé approximation method. So if you recall from the Padé approximation method, we have a rational function and we want to approximate a given function f. And our rational function has a total of capital N, which is a degree of the rational function, plus 1. Because actually it's supposed to be capital N plus 2. We reduced by 1 by assuming that the denominator cannot be 0. And for that purpose, if the denominator cannot be 0, in the neighborhood of 0, it means that we can assume Q0 to be non-zero, and we explain why. And if we can assume that Q0 is non-zero, because 0 is the interval about which we do the expansion of f is 0. That's why we use the Maclaurin expansion. So we want to make sure that at 0, Q0 is not 0, beside other roots. At 0, Q0 will never be 0. So that's why if you substitute Q0, I mean Q, the denominator, at 0, it will give you Q0. So if you don't want it to be 0 at 0, then we can assume that Q, the constant coefficient of Q, which is Q sub 0, we can assume that it's non-zero, and for that we can factor the numerator and the denominator. By that and cancel out. Therefore, that leading factor, I mean that constant coefficient will be 1. So by so doing, we reduce the number of unknown by 1. Okay. So the degree of the rational function is capital N, which is m plus n, where n is the degree of the numerator and m is the degree of the denominator. So in practical problems like tutorial exam, if you are asked, for instance, like in the example that we tackled in class last time, when we say you are asked to determine the fifth degree Padé approximation of a given function. Fifth degree means that capital N, which is m plus n, is equal to 5. So the values of the degree of the numerator and that of the denominator have to be specified so that you will not be confused. Because if you just say the fifth degree, what does that mean? Does it mean that the denominator is 2 and the numerator is 3, or the numerator is 3 and the denominator is 2, or it is 4, 1, and so forth? So there are many combinations, so you will not really get your head around it. So that's why generally the polynomial, the rational function, or the Padé approximation will be subscripted with 2 indices. The first one is the degree of the numerator. The second one is the degree of the denominator. So I explained the strategy. The strategy is to impose a condition on the error. The error, because we want to approximate f of x, the error is f of x minus rx, which is the Padé approximation of f. So that error, we want to impose some restriction in such a way that this restriction will allow us to compute the coefficient of p and q. That is the polynomial in the numerator and q, the polynomial in the denominator. So we saw that we can impose that the multiplicity of the error at 0 is capital N plus 1. So if it is capital N plus 1, it means that all the derivative of that error, that is f minus r, at 0 is 0. So by imposing this, we came to the realization that the numerator of the numerator of our rational function, when we expand it, all the degrees of xk for k less than or equal to capital N have to be set to 0. And that is a linear system that we obtain because the total number of coefficients in our rational function is capital N plus 1. And if we set the degree of xk for k running from 0 to capital N, it will give us a system of n plus 1 equation. So we have a system of n plus 1 equation and in n plus 1 unknown, which are our P0 up to Pn and Pn, and then from Q1 up to Qn. So it gives us a total of n plus 1, which is capital N plus 1. So that's how we obtain our linear system. And once we obtain that linear system, there's a strategy. You can obtain a linear system, but if you don't know the strategy on how to solve it, you get everything wrong. Sorry. This is not what you're supposed to share. Let me see. Yeah, it's this one. Sorry, I'm in a class. I'll get back to you.
All right, though.
Okay, so this is what we have. So this is the error, and this is its numerator, right? And that numerator is expanded here. So by imposing this condition up to capital N, we saw that 0. Of course, this one I was explaining. Okay, I was explaining. Okay, so for our case, I see that there's a strategy to solve that linear system. So I will share the corresponding slide, because this slide is not the one I'm supposed to use to illustrate. Even though I can use this, but I want to go straight to the example. So let me share that. Okay, so I was saying that once we obtain our system, there is a strategy on how to solve it. Because if you don't write the proper strategy, you might get the correct system, but not being able to solve it properly. And if you cannot solve it properly, you will not get the final result correct. So that's why I'm insisting that you should really take that into account, because it's very important to know the technique that is being used to solve that linear system. Okay, now let me share the screen. Let me share this. Okay, so this is the example. This is the example that we tackle. Now here we are taking the degree of the numerator, which is n, to be 3, and that of the denominator to be 2. But recall one thing, is that the degree of the numerator is what you will equate, because when you set the numerator to be 0, the right-hand side of your equality will be the polynomial in the numerator, which is this one, the p's. The p's will be on the right of the equal sign. And the p's, sorry, and the q's, right? Because you can see from here, the q's mix with the coefficients of f being the polynomial that we are trying to approximate. This one, the coefficient will be mixed here on the left. Now, and don't forget, when we expand this one, we expand in such a way that the degree goes up to capital N being this, the degree of our Padé approximation. Now, you will agree with me that if the degree, and generally it will be less, right? Because this one, remember that it is the sum of the degree of this numerator plus the degree of the denominator, which is 2, that gives us 5. So meaning that in this expansion, when we equate these two, there will be coefficient here that will be set to 0. And the number of coefficients that will be set to 0, in general, will give you the number of unknowns in our denominator. If you look at this expression here in the denominator, which is our q, you see that there are two expressions, q1 and q2. And these are the two coefficients that we need to determine first before we can get the p's. You can see that these two, because there are two unknowns, we also add 2 here to the 3 to reach the 5. Therefore, in our system, the two last equations will be equated to 0. And that's what will give us our linear system in Q. So we will always start by solving our linear system in Q before substituting it in the remaining equation in the system that will contain P. Because this P, you see that if we equate, you will see that P will be equal to a function of Q, meaning that I need to compute Q first and substitute in the equation to get the values of P. And that can be seen here. You can see that if we equate, we say P0 equal to 1. Of course, if we equate from right to left or from left to right, it doesn't matter because we can still rearrange. So you see that we can write these P's in terms of Q's. And the last equation that will be equated to 0 will not depend on P, because I need to add extra coefficient here to equate to x4 and x5. So there will always be coefficient that I will add to the P's to equate to the left-hand side. And those ones that I will equate to 0 are the ones that will contain only the Q's. And those are the system that I will solve first. So you can see it from here. There are two extra coefficients that I will add here to reach the degree 5. Because this is 3, I need to put 0x to the 4, 0x to the 5. So there are two extra coefficients, 0 coefficient that I will add here to equate the right-hand side polynomial, a left-hand side polynomial. And if I do that, you see that there will be two equations that will be equated to 0, even though, of course, this is a constant coefficient that I will still set to the other side and solve my system of two equations in two unknown. I always start, you always start from this last equation that you equate to 0. When I say equate to 0, it's from this equality. And then you take the constant coefficient to the left and write it properly so that you can solve your linear system. And this will only contain Q's, not P. Because see, the P's depend on these two, Q1 and Q2. They depend on Q1 and Q2. So you can see that Q1 and Q2, Q1 and Q2, Q1. They are there. So you first need to obtain their value before you can substitute and get the corresponding values of P. If you don't do that, if you try to start from the first equation here on top, you will never make it. Your result will always be wrong and you will always be confused with this. So the methodology, understanding the methodology is really crucial, because once you understand this will become a game to you. It will become a child game. Now, I hope it is clear. If you don't understand, you can stop the video, rewind it, and listen over and over again. Very important to understand this. And it will always come. This Padre approximation will always, in test 1, it will be there. And surely during the comprehensive test, I think so. So you need to know this to be sure that you will get the marks. Make sure you understand this and you can solve any related problem. Okay, now to illustrate, you can see that we first found here in our example Q1 and Q2, right? By just doing what? By solving this. There are many methods. You can use Cramer's rule, you can use a substitution method, you can use a Gauss elimination, right? Gauss elimination would be more efficient if you have a system, you have the system in Q1, Q2, Q3 or above. Then Gauss elimination will be faster for you to. So we first need to compute a Q, and that's what we have here. So once we compute the Qs, we substitute back into the expression of P1, P2, P3, and that's what we did here. We got the result. And once you do that, you substitute back into your equation and you get your result. Okay, now, this is what we obtain. Now I will motivate continual fraction. I will motivate why we need continual fraction at this stage. Okay. If you recall, I think I can share the other slides before coming back to this. If you recall with polynomials, when we faced the issue of evaluating a polynomial at a particular point, we saw that if we have a polynomial of degree n and we want to evaluate it at x0, the number of addition to evaluate will be n. That is the degree of the polynomial. And the number of multiplication will be of the order of n squared, which exactly will be n times n plus 1 by 2. That is the complexity, meaning that it's a quadratic. It's the number of operation is quadratic in n, in the degree. The larger the degree, the larger the number of floating point operation, particularly the number of multiplication. And a way around this was okay, since there are many, in fact, it's quadratic, the number of floating point operation is quadratic. How can we circumvent this? The solution was the nested form, or the Horner form. That is, we write it, we use a nested form to express our polynomial, and then we are sure that at the end of the day, the number of multiplication will also be n. That's what we did during the first semester. Now look at this expression. If you look at this expression, if you want to compute the complexity of this one, the number of floating points, but particularly the number of multiplication, because we know that the number of addition will be equal to the degree, right? The degree of this. Now, if you want to compute the number of floating points, particularly the number of multiplication of this one, it will be exactly the complexity of the numerator as a polynomial plus the complexity of the denominator as a polynomial. Meaning, since we know that the degree of the numerator is n, is n, not m, is n, let me write it aside. Therefore, for the numerator, the complexity will be m into m plus 1 by 2. That is, it is quadratic in m. Similarly, for the denominator, it will also be quadratic in m. So at the end of the day, it will be quadratic because we'll be adding 2 quadratic, the complexity of 2 quadratic. The resulting is still quadratic in the maximum of m and n. Meaning that, like in this case, the degree of the denominator is 2, the degree of the numerator is 2. So it will be quadratic in 3. That's what it means. Because we'll be adding a second degree polynomial. What am I saying? Yeah, we'll be adding a second degree polynomial plus a third degree polynomial. So that's the complexity. Now, what can we think? Since here, if we write the nested form in the numerator, nested form in the denominator, it might be an idea, but it will not be efficient. That's a possibility, but the best way to solve that problem is the continuous fraction. Because with the continuous fraction, we'll be able to write this numerator and the denominator in a form that will be simpler for us to evaluate. So that's the idea behind the continuous fraction. So I repeat, similarly to the nested form, of course, nested form allows us to reduce the complexity of the number of, the floating point operation when evaluating a polynomial at a particular point. Now, if you want to do the same thing with Rx, you can see that it is really complex, right? Now, if you want to reduce the number of floating point operation here, particularly the number of multiplication, because multiplication is more costly compared to addition. So we use continuous fraction to reduce this number of operation. So roughly speaking, that is the case here. So let me compare before we dive into the continuous fraction. I would take the continuous fraction expression of this. We will compute the number of addition and multiplication for this one, and I will show you the continuous fraction form of this, and we will also compute the number of addition and multiplication. You will see that there will be less multiplication in the continuous fraction expression compared to this one. Okay, now let me write the number of multiplication here. So for this one, theoretically, there will be, so theoretically, when I say theoretically, I just assume that this is a third degree polynomial. This is a second degree polynomial, and then I count the number of multiplication and addition. So we can even do it here directly. This is 1 multiplication. No, it's 0. It's not even 1. There's no multiplication here. It's 0. So I can count that this is 1. This is 2. This is 3. So in total, we have 6 multiplication here. 6 multiplication. So theoretically, A in the numerator okay, 1, 2, 3, 3 addition and I say 6 multiplication, and in the denominator 1, 2 addition and 3 multiplication. So in total, here, in total, how many? So in total, we have a total of 5 addition and 9 multiplication. 5 addition, 9 multiplication. Now let us go back. Let us not back. I mean, let us go to. Let us go to the approximation, the Faraday approximation of this. Sorry, continuous fraction form. Continuous fraction form. Okay, this is a continuous fraction form. You can see it's exactly the same thing. Now here in the continuous fraction form, let us count the number of addition. So here, sorry. Okay, now if you count, let us count. Number of addition, this is 1, 2, 3, 4, 5. So there are 5 additions here. 5. 1, 2, 3, 4, 5. 5 addition. How many multiplications? This is 1. Of course, I can count this because x is, that's theoretically, yeah? Theoretically. Because the coefficient here might be non-zero. Like here, you can see this one. I can take this 3 in the denominator, then I will multiply everything here, right? Because this, it was just a simplified form. But actually, when you have this 3 should come and multiply the term here inside. Because we know that this expression will be of the form of ax. So theoretically, this is another multiplication, and this is another multiplication. So there will be 1, 2, 3. 3 multiplication. So this one, theoretically, I don't count this. I don't count this to be like division or multiplication or something, because this term can be written as ax plus b. You see that this b is just a number that is there, right? Because in the computer, this will be a number, right? So when you look at this theoretically, this is a one multiplication, one addition. Similarly, this is of the similar form. So you say one multiplication, one addition. And finally, this one also will be of the same form, ax plus b. So theoretically, there will be, I've already said it, 1 addition, 2, 3, 4, 5 addition, and how many multiplication? 3. 1, 2, 3 multiplication. So theoretically, that's what we have, theoretically. Theoretically, it means that you write it in the general form, right? Theoretically, because in some cases also this coefficient might be 0. If that is 0, so when you say theoretically, that would be the maximum. Right? That's the worst case. The maximum will be this number of addition, that number of multiplication. It may also happen that this term for some will be 0. So theoretically, this is the number of addition. 5 addition, 3 multiplication. Then now let us go back. So here it is 5, 3. Now above, when we computed how many were there, I think we had up to 9 multiplication, if I'm not mistaken. You see, 9 multiplication, 9 multiplication, 9 multiplication. Whereas previously it was 5, 3. So you see that the number of addition is being conserved, right? Similarly, even with polynomial, when you move from the general expression of polynomial to the nested form of the polynomial, the number of addition does not change. It's still n, right? And 5 here, if you recall, is the degree of our r. Remember that here the degree is 3 plus 5, which is 3 plus 2, which is 5. So the number of addition in general is equal to the number of, it's equal to the degree of the polynomial. You see, it's still 5. Now, this, which is 9, is reduced. Right? It's reduced. It's reduced. Now, let us see if this formula will give us something similar to. Now, if I say it should be n into capital N plus 1 by 2. And we know that n is 5. N is 5, right? So this will be 5 times. So now this one is 6 by 2, which is 3. See, if I add this, it's 5, which is this one, and this is 6 by 2, 3, 15. So which is not the same, right? Which is not the same. So it takes it's not the same with polynomial, because this is a fraction, a rational function. Okay, so we have 5, 9 here. That is 5 addition, 9 multiplication. Whereas here we have 5, 3. 5, 3. And 3 is the minimum. No, 3 is the maximum, eh? 3 multiplication, which is the maximum between this degree and that one. So now you see the advantage of using a continuous fraction to simplify this expression. This is easy to evaluate using the computer compared to the previous one, compared to this expression here. So that's the motivation. So this is against 5, 9. So you see that there's an economy of 6 multiplication. Okay, Now, this being said, this is a good motivation for us to study continuous fraction. Okay, now continue fraction. Okay, now let us dive into continuous fraction. First of all, we'll define continuous fraction numbers. Look at the expression in 1.26. If you look at the expression, this expression how it's written. You have an integer plus, now you have a large bar, and everything else will be under one over that bar, because all this is a single expression, right? In fact, all this is the denominator of 1. Now, in this denominator, we proceed. That's why we call it continue. So this is a fraction. 1 by is a fraction. But that numerator, we keep fractioning it. You see? A1 plus 1 by another fraction. A2 plus 1 by. So here we stop at A3. If you look at the first one, A0 plus 1 by A1. A1 is the last sequence in our expansion of the corresponding real number into continuous fraction. Okay, if you have A0, it means that the actual number is an integer, right? If your number is an integer, its continuous fraction is equal to itself. So any integer, you can see here where A0 is an integer. So let's say, for instance, you want to write the continuous fraction of -5. It will just be A0. You cannot proceed. You stop there because you cannot write it as a fraction again. It's an integer. So A0 is that integer itself. But now, if you want to expand a fraction, let's say a fraction. If you want to expand a fraction, like what? 1/2. 1/2 is already in the continuous fraction form. Because for 1/2, since it's a fraction, your A0 will be 0. And your A1 will be 5 for a rational number, for instance. Now, if you have a real number, now it will depend whether that real number, because when you say real number, there are real numbers that, like pi. Pi, you see, the decimal part is recurrent, right? It repeats indefinitely. It does not stop. You see that for that one, this continuous fraction will not also stop. It will continue, you write this, you will continue to infinity. Okay, now, if your continuous fraction is a rational number, you'll be able to write it this way, using a finite number in your sequence. So let us look at the definition. The continuous fraction representation of real numbers has several desirable properties. Some of which are, the first one, the continuous fraction representation for a number is finite if and only if the number is rational. That's exactly what I just said. If your number is rational, you have a finite representation, right? If it's finite, if it is a rational function, you have a finite representation. But if it's irrational, then you'll be able to write it indefinitely. Okay, every rational number has an essentially unique continuous fraction representation, meaning that if we are 100 and we are given a rational number to expand in continuous fraction form, all your coefficients here, A0, A1, A2 up to AN, because it will be finite, will be exactly the same. They should not differ. So the representation should be unique, right, for a rational number. Okay, the terms of the continuous fraction will repeat if and only if the continuous fraction representation of a if it is the continuous fraction representation of a quadratic irrational, right? Quadratic irrational. You see that it has to be irrational already. And quadratic irrational means that it is the real solution of a quadratic equation with integer coefficient. For it, it means that you have this irrational, let me call it R, I for irrational, or I sub R. It has to be solution of something of this form. Okay, I will use n. Okay, let me call this n2 x squared plus n1 x plus n2 equal to 0, where, oh, sorry, this is n0, where n0, n1, n2 are all integers, right? Of course, and n2 is non-zero, right? When I say that they're integers, okay, let me say n2 different from 0. Because if m2 is equal to 0, it's no longer quadratic, right? So this is what it means. So if you have continuous fraction that repeats, right? That repeats, it means that the number that you are expanding in continuous fraction form is a solution of such a quadratic polynomial where these coefficients are integers, right? That's what it means. Okay, now this is the algorithm. How do you proceed now? That should be the obvious question. How do I write the continuous fraction representation of a real number? This is the algorithm. First of all, what we do, we take the number, we write that its integer part, which is denoted by R. No, sorry. Its integer part is I. You see, it's not R, I. This you can see here. So we write down the integer part of R, the real number, I. We write it down. For instance, if R is 3.75, right? The integer part I is equal to 3. That's what it means. You write this 3 down, you write it down. Now you subtract the second part, you subtract this integer part from R. Second part, this one. So I take R minus I. This will give 0.75. This is what we get. And this is the fractional part. That's what we call F. The fractional part. And then you take the reciprocal of this. Of course, if the difference is 0, you stop, right? If the difference, that is this difference, R minus I, if it's 0, you stop. But here is non-zero, you proceed. And how do you proceed? You take the reciprocal of this. So you take 1 by F, right? If you take this, this is 75%. And what is 75% is 3/4. So 3/4, if you take the reciprocal, is 4/3. You see? This is what you will get, 4/3. Now, 4/3 is a real number, right? It is a real number. Now, you have to proceed all over. This is a real number, right? It's a real number with a non-zero integer part. So from this, you have to start all over. That is, you go back, you assume that it's a new R, you compute this real part, I mean, you extract the real part, and then the integer part, I, the new I, and then you subtract. If the difference is 0, you stop. Otherwise, you take the reciprocal, and you continue until the difference between the real number and the integer part is 0. Then that's when you stop. Okay, so what is this is equal to 1 point, and it repeats, right? It will repeat. Okay, let me put it ellipsis to say 1.333333. So 3 will repeat indefinitely. Okay, so this is where we are with this. One point 33333, and okay, so we repeat the same process. Now the integer part, the new integer part will be 1, and the fractional part will be 0.33. So you keep doing that. So let us look at a particular example. Let us look at this one. 9 by 7, or 9/7. 9/7 is 1n to 7. This is the integer part, and this is the fractional part. So it's similar to what I wrote here. This one, 3.75, we can write it as 3 and 4. So what I mean is this one, we can write R equal to 3.75 as, so this is 3 point, the fractional part. And when we say 3 plus this, it will be 3, and then we take this 3, 4, 3, 4. This is the fractional part. So 3.75 can also be written like this, because if you add these two, it will give you that. Right. Okay, so that's what we have here. So this is our number. Directly we read the integer part and the fractional part. So we have the integer part and the fractional part, which is this. And then we take the reciprocal, it gives us this, and we write it again as our new real number, and we repeat the process. So we take it back here, because this is our real number. Take this reciprocal, which is a real number, we take it back, and we repeat the process. That is, we take the integer part, and then we take the fractional part. And the reciprocal is 2. Now, since the real number is already an integer, we'll stop. Because if we take it here, you can see that the fractional part is 0. When we take the real part and the fractional part, which is 0, we stop. Because remember, we say we stop when the fractional part is 0 here in the algorithm. If the difference, of course, which is the fractional part, is 0, we stop. And that's what we have here. We stop. Now, once we stop, we collect now. We collect everything. Everything, meaning we look at, we come here under the integer part, we collect all the integers, right? Because remember that in the continuous fraction here, A0 is an integer. It can be positive or negative, but the remaining, that is from A1 up to AN, they have to be positive integer. Right. Let's say, for instance, if my R is negative 1. Let's say 2.25, for instance. You agree with me that my A0 will be negative 1. Then my fractional part will always be positive. So if I proceed from here, the remaining coefficient A1 will always be positive because it will come from this. So that's why in the definition, A0 is just an integer. If the real number is positive, A0 will be positive. If the real number is negative, A0 will be negative. But the remaining are always positive. So that's what this means. I hope it is clear for everybody, or you will be clear for everybody. Okay, so we collect, because they are all integers, they are all integers. All these, they are all integers. And this will come from the integer column, right? This one, integer part. So this is our A0. We write it here. And then A1, finally A2, which is this one. So A0, A1, A2. A0, A1, A2. So actually, this one is just supposed to be written as 2. Not like this. This is 2. Because we have 3. 1, 2, 3 terms. 1, 2, 3. And that one has to be written as is. This last, you don't break it. It is 2. So please change it on your slide. I hope it's not. No, I think you have it. So please write this. This is 2. This should be 2. The number of element here in your column, the integer column, this one, 1, 2, 3. That number gives you the number of terms that will appear here. So we have A0, 1, A1 is 3, and finally A2 is 2. And this should be the last denominator. It will end by 1 by A2, as you can see here. You can see that here we have 1 by A2 when there are 3 terms. In our representation, there are 3 terms, A0, A1. You can see that here we didn't break this into 1 or whatsoever. It is exactly the number as it is there. If there are 4 terms, A3 will be the last one in the denominator. Please correct that on the slides. I corrected it last year, but I did not update the note. That's why it's still appear here. So this will be 2. All right, the next example is the second one. We do the same thing. We have integer part, fractional part. We write it there, and then we take the reciprocal, write it in this form, which is a real number, and we repeat the process. So we take this, copy it there under the real number column, then take these 2, put there, and take this reciprocal, the reciprocal 49/4, which can be written in this form, 12 1/4. So we take it back there, the real part, the integer part, and then we take the reciprocal. Once the reciprocal gives you an integer, you are sure that you'll be stopping after that. So we take the 4 there, we repeat, because you can see that here the fractional part is 0. Once we express fractional part is 0, we stop. We stop. And then we come back to the integer column, integer part column. We have 1, 2, 3, 4. So our continuous fraction will be represented by these 4 numbers. This is A0, A1, A2, A3. A0, A1, A2, A3. And that's what we will write. So we'll be ending the last fraction will be 1 by A4, which also here is 1 by 4. So you have all the terms. That's A0, A1, A2, A3, which is 4. So that is the continuous fraction. So, okay, so that is for continuous fraction. This can be repeated for any number. So you understand, once you understand the methodology, that is something similar. Something similar will be also performed when it comes to function, rational function. We start with real numbers and then we move to rational function. Okay, so I will stop here for today. It is likely that I record another one, maybe over the weekend or by Monday. If I don't record, therefore, we'll meet on Monday to go through this. But I can already encourage you to read this part to prepare for the next class, right? It's first better for you to digest this and try to repeat all these problems on your own. And you can take any other number. Now, to be sure that your expansion is correct, it is simple, right? It is simple for you to check that if you take an arbitrary number, you expand, it will give you the correct answer. Now, let us check. That's where I will end. Let us check that this will give us that. So easy. We take the last, this last fraction, we add these 2 numbers, right? So if we add these 2 numbers, what do we get? This will be 7/2. This is 7/2. 3 plus 1/2 is 7/2. If I cross multiply, 2 times 3 will be 6 plus 1, 7 by 2. So this is 1 plus 1 by 7 into 2, which is 1 plus 2, 7, right? And which is exactly this one. Or if you want, this is 7 plus 2, 9, 7. So it's the same as 9, 7. So you can always check, right? So when you get your result, please check. Don't be confused. Oh, is it correct? No, you can always check. 2 numbers are equal if and only if they're equal. That is, you expand, you reduce the right-hand side term until you get this, until you get the left-hand. So you can do the same thing here. Add these 2, get the result. Once you get the result here, you add with this one, you get the result, you add with that one, and make sure that you get this at the end. That's all. Okay, thank you for your kind attention. Is there any question before I stop? So far, so good. Okay, so if there is no question, we will stop here. God bless you. Have a blessed weekend. And check if I will update or upload a new video. Otherwise, see you on Monday. Bye-bye.